Hello everyone and welcome to Numpy full tutorial. So at first, Numpy stands for Numerical Python, featuring powerful capabilities such as dealing with large arrays or matrices, matrix multiplication, comprehensively accessing the elements, slicing, array selective sorting or selective search, filtering, etc. So it is mainly used in linear algebra, matrix operations such as transpose, matrix product or dot product. Dot product means element by element, okay? And also used in prominent applications such as in the artificial intelligence field, as it handles large data sets. Now, what we need to note here is the array in NumPy is different than the array in Python in general. Python array is not actually an array but a list that acts as an array when it's numerical. However, for NumPy, the array has different applications, different operations that are not applicable for native array version. And in NumPy, you can do things that you cannot do in native Python list. It's a list actually in the native language. Among the operations is casting an array from Python to NumPy array, where you can start to deal with the operations that are specific for NumPy. Alright, so here is an example of casting a list into an array. Okay, now it might not be very explicit. However, what you see on the inside, 1, 2, 3, 4, 5, delimited by 2 square brackets, is the same definition of a Python list. Alright, so it's like casting a list into an NumPy array. So how do you declare an array? A equal np.array 1, 2, 3, 4, 5. Okay, delimited by square brackets. This is a one-dimensional array. Now, for two-dimensional arrays, you have A equal np.array 1, 2, 3, 4, 5, 6. What do we have here is actually two main elements. Each one of the elements is an actual vector or array itself. So you have two arrays being two elements within another array, or an array within an array will give you something like a matrix, okay? Or a multidimensional array. In this case, you have a two-dimensional array. So in this example here, what you have is two elements, both of them being vectors. So each one of these, whether 1, 2, 3, or 4, 5, 6, are an element or an array, and each of these two arrays is actually an element within this larger array. So 1, 2, 3 is actually the value of A at index 0, but at the same time, this value is an array of its own. If you print A at index 0, it will give you 1, 2, 3. By the way, that would be 0 and that would be index 1. So at index 1, if you print A at index 1, it will give you 4, 5, 6. So it's an element, but this element or this value is actually an array of its own. So the second element of A, which is at index 1, because arrays start from index 0. It's a rule of thumb. So if I print A0, it will give me, as I mentioned, the first element, which is a vector, not one value, because here it is two-dimensional. Now, let's say I want to get not only the first row, and by the way, here you have two rows if we're talking in matrix language. Not only I want 1, 2, 3, but out of 1 to 3, I want specifically value of 3. You need to note that in A, you have two elements, two main elements. This one and this one. 1, 2, 3 is the first, which is at index 0. And 4, 5, 6 is the second, which is at index 1. If I print A0, it will give me 1, 2, 3. However, what if I need not the entire row, but only 3? To access value 3, which is located at the first element of A, namely 1, 2, 3, and on the third position of the vector, which is 1, 2, 3, you print A0, 0 alone will give you 1, 2, 3. Then 3 is at which index? You have 0, 1, 2. At index 2, it will give you 3. So print A02 equal 3. So at the first level, meaning that when you have a two-dimensional array or n-dimensional array, at the first level, meaning this is the first vector here, those two square brackets on the outside, you have two main elements. This is the first one at position 0 or index 0, and this is the second one at position 1. So let's say I need to get this value here, 40. You type print A. Now 40 is on the first row in the first element, which is at index 0. So print A 0. Then within 0 you get 40, which is at the third index. So print A 03 will get you 40. Now here in this example you have print A 1 3. 1 is the second element, the value at position 1, which is this vector here, 50, 60, 70, 80. Okay, so print A1 alone will give you this line, but A1, 3 will give you, out of this line, out of this vector, the value at index 3, which is 0, 1, 2, 3, 80. So A13 would give you, index 1 is this position here. Here you have this value at index 1. So at index 1, I need to access element at the third index. So A13 would give you 80. Alright, A11, that is position 1, index 1 on the outside, this larger vector, and then on the inside. So among all the elements of this, that is the value at index 1, which is 60. Another value for A entirely, that is index 0. Print A0 would give you this row. Now, inside this row, I need to access index 2. So 0, 2. 30 is at 0, 1, 2. Now, getting back to one-dimensional array, and we're talking about slicing, like sectional extraction of a vector or a matrix. Let's say I need to get, starting from the second index, all the values up to the end. So you simply type print A, you open braces, 2, colon, and nothing afterward. Meaning that, give me every element starting from index number 2. So 0, 1, 2, that is the value at index number 2, which is 30. And it will give you all the way up to the end, which is all the way to 80. Alright? Now, another example for slicing. Let's say I need to get the elements from the third index to the sixth index. Now here we need to pay attention because it might be a little bit confusing. So to get all the values starting from the third index to the sixth index, you might think that I need to type A3, 6. However, if I need to get all the values to the sixth index, the other edge, like the other part of the interval, which is here, should be 7, because always the last part would not be included, which makes sense, by the way, because if I needed all the values from 3 up to the end, I wouldn't use this formatting. I would rather use 3 and column without anything afterwards. However, when you need all the values from the third index or from index 3 to index 6, you type print A 3, 7, and it will count 3, 4, 5, 6 without the 7s. And you see here you have 40, 50, 60, and 70, and we will show you how it works in the practice. Another interpretation for that, by the way, is as if you're telling Python compiler, start from the third, go up in a way that everything from the beginning would count 7 elements. How many are 7 elements, 7 values? It would be 0, 1, 2, 3, 4, 5, 6. Start not from the beginning, but from index number 3. Now, negative indexing. You've seen the conventional indexing starting from 0 up to 7 here in this example. If I need to print the last element of A, I can either refer to the index of that last element, A7 would give you 80, or there's another way, because if you have a very large array, how can you tell what is the index of the last value? Another workaround is print A index minus 1. Index minus 1 refers always to the last value at the last index of an array. Another way to see that is looking at these indexes, called, by the way, negative indexing. It is another way to refer to the elements within an array. As we mentioned, minus 1 refers to the last value inside an array. Minus 2 is the one right before it. Minus 3 before it, all the way. So at the beginning it would be minus 8, minus something. But note that cannot start from 0 because 0 is always reserved to the first one on the left. So print A minus 2, which is this index, it would give you this value, 70. Negative slicing, another way to look at it, we can reference the values or the elements within an array using their negative indexes from the right to the left, of course, by -1 or -1, which would be referring to the last value, then -2, -3, all the way to the beginning. Of course, 0 is reserved to the first value to the left. So if I need to get the elements or values from -4 to -2, in the same way, you simply type print a -4 up to -1, which is right after -2. And the value at -1 wouldn't be included. So it will give you 50, 60, 70, which makes sense. Let's say if you needed all the values from -4 all the way to the end, you wouldn't type -1 here. You would leave it empty, okay? Because -4 column would give you everything starting from the -4 index all the way to the end. Here, however, it will give you everything starting from -4, but it would not include the value of -1. All right? Another way of slicing arrays. So let's say I need to get the values under 1, 2, 3. So here you have two-dimensional array. You simply type print a, 0, 0 would give you all of that row. However, if I need to start from index 1 to the end, while excluding value at index 0, you simply type 1 column. This would give you 20, 30, 40. This is how you can access multiple dimensional array. So 0 is referring to the first level, which is this value here. It's like an element within this larger array. So in large, the first array is this one, the square brackets to the outermost. Then you have this acts as an element within that array, but it's an array itself. So 0, comma. Then within that second array, I need to get all the values starting from index 1 all the way to the end. So 1 column would give you 20, 30, 40. Also, a similar example for that, I need to print the value at index 1, which is this row, not all of it, only 60 and 70. At first, if I print A1 without anything else, it will give you this entire row. That's the value at index 1. But if I need to only get 60 and 70, they sit between the first index and second index. You type 1 colon 3, not 2, because 3 is the edge. It won't be included. So to get 2, you need to type 3. It will get 1, 2 all the way to 3, but 3 closed out. It won't be included. The value would be 60 and 70. Now in my practice, I'm using PyCharm with a dog team. At first, in order to import Numpy, you need to have installed the package of the Numpy library. You go to Python packages, type Numpy, then you click on install. You see here it's already installed. But in case you didn't have Numpy, you install it via this menu over here and you will have Numpy immediately. So go back to run, import Numpy as np. To declare an array, ar equal np.array. You fill within it a list. Actually, this is a list inside the array. 2, 4, 5, 6. Print ar and you have the array. To create an array out of a tuple, you simply do ar equal np.array, and that would be the definition of a tuple. 2 parentheses, 1, 2, 3, 4, 5. Print ar, the same thing. So let's say you have a tuple here, t equal 0, 1, 5, 6. We can make an array out of a tuple. This is a tuple here. So ar equal np.array t, and you will have the same thing. Let's say I want to create multidimensional arrays. So what are multidimensional arrays? They are arrays within arrays, okay? So here, if I print the dimension of ar, let's say ar.ndim, or number of dimensions, is a one-dimensional array. Why? Because you have only one row of elements. In order, however, to create multidimensional arrays, let's say 2 dimensions, this is how I can declare it. So a equal np.array. So at first, this is the first dimension. And within that dimension, I have another array for each element, okay? So within the array, I'm gonna have 2 arrays. So 1, 2, 3, then 4, 5, 6. If I print a, you have 2 lines, each line being an array. So you have 2 arrays inside the same array. In other words, a matrix. And each element being 1 line. So here it is the first line, here the second line, and here, for instance, this element is the second element on the first line. So its index is 0, 1. 0 being the first line, because each element within an array is indexed at 0 on the first position. Then you have 0, 1, so it is the second element, but its index is 1 on the first line. Another multi-dimensional array example. So let's say you have b equal np.array, and we're going to create 3 dimensions here. You need the first dimension. Now each element of this first dimension is an array, and it also contains another array on the inside. Okay, so that's the second dimension so far. Then within this array, within each one of them, you have another array, of course. 1, 2, 3, 4, 5, 6. And you see, PyCharm is intuitive. It gave me the entire array. If I print b and I print the dimension of b.enddim, let's see what happens. And you see, we have a matrix of 3 lines, each line being 3 elements. So this is a 3D array. 4 lines, 3 columns, and the dimension is 3. Another way to create an array is duplicating one line multiple times. Okay, so let's say I want an array in which 1, 2, 3 is located on 3 lines. T equal np.array 1, 2, 3, and the mean, not enddim, is equal 3. Let's check 3, print C. We have 1, 2, 3 repeated 3 times. Now array indexing, how to access the elements of an array. So let's declare at first AR to reinstate the one-dimensional array. So AR equal np.array 10, 11, 12, 13, 14, 15, and 16. Now, if I want to access the first element, I simply do print AR 0, that's the first element. And the first element at index 0 is 10. So if I want to access the fourth element, 0, 1, 2, 3, it will have index 3. So AR 3, it is 13. 0, 1, 2, 3. Now, let's say I have a multi-dimensional array. Let's comment this one. Going to a 2-dimensional array, if I print A 0, it will print for me the entire first row. Because simply, as you see, the first row here is the first element of the array. The element of array A is actually not only one number, but a vector itself, which is an entire line or an entire list of numbers, if you will. The element itself is an array. Now, if I want to extract a specific number of that internal array, print A0 will give you the first line. But I want out of the first line the second or third element. So, to print the third element, I simply type comma, then 0, 1, 2, and it gave me 3. Now, another way to do that is actually typing 0, minus 1. Minus 1 means give me the last number of this internal array, which is 3. So it gave me 3 as well. If I want to go to a multi-dimensional array to extract values, so here I have multiple dimensions, actually, 3 dimensions, correct? So an array within an array within an array. So how to deal with it? Let's say I print B0. It gave me this first entire block completely, because this is element 0 of the entire array. Element 1 is this block. And as you see, you have arrays within arrays. You have an array within an array within an array. So this first line, if I need to extract, let's say, the first block. So here you have 2 lines, like a matrix, as an element within this array. Out of this matrix, I need the first line. Print B, 0, 1. Let's check it. Here you have index 0, and here you have index 1. Okay, so index 1 would be the second value, the second element, which is the second line. But if I type B0, 0, it will give you 1, 2, 3. I'm still printing here a dimension or something. Let's comment this one. Now let's say I need to get this value 7 here. So how to approach it? How to actually extract 7? At first, where is 7 located? That's the question. On the external, on the first level, which is the first dimension, if you will, you have 2 elements. This one at position 0 and this one at position 1. 7 is located at position 1. If I print B1, it will give you this entire block. 7, 8, 9, 10, 11, 12. Now, 7 is located at index 0 of this second block. Index 0 meaning the first element of this array here, this inner array. If I print B1, 0, you will get 7, 8, 9. Then, within 7, 8, 9, I need to extract 7, which is at position 0. So I simply type 0, and you will get number 7. And of course, so on and so forth. You can have multiple dimensions for an array. Now, another thing, we can actually address the arrays using negative indexes. What do I mean by that? So if I go back to the first array, which is a one-dimensional, because the example would be more simple. For this one-dimensional array, if I print AR minus 1, what we will get is the last value. And by the way, you have the index of the last value at the end is minus 1, the one next to it is minus 2, minus 3, all the way to the beginning. So print AR minus 1 would give you 16. Alright, now let's say I need to get a section out of this array, meaning a part of this array, okay, not all of it, from the second index all the way to the end, or from the second to the third to the fourth, or from the 13th all the way to the end, from the beginning up to the 13th. You can call it a sectional extraction, or technically it is called slicing. So how can we do that? So let's say I need to print from the second element all the way to the end. Okay, so print AR2, meaning get me index number 2, which is this one, 0, 1, 2, all the way to the end. And you see 0, 1, 2, starting from 12, it got us all the part to the end. If I need to extract from the first up to the fourth element, print AR from the second index, which is index 1, 0, 1, 2, 3, up to the third index, which is not included, by the way. So if we want to get from index 1 up to 2, 3, I need to get him 4 here, because the last one, the last argument, won't be included. The fourth is not included, so we needed to get him 4. Starting from index 1, cover all the elements in a way that all of them would count for elements. Let's say I need to get everything up to the 5th element, so print AR, start from the beginning all the way to the position 5, which is not included, meaning that cover only 5 elements. So let's see how it works. It covered 5 elements, okay? The 5th index is not included, so 0, 1, 2, 3, 4. Index 5 is not included, as you see. It's important to notice that. If I print, let's say, A and column, it will simply print everything within the array, as if you're saying print from the beginning all the way to the end, all the elements within that array. Let's work now with negative indexes. As we mentioned, minus 1 is the last element of an array. So if I tell him, get me from minus 4 to minus 3, minus 2, but all of these should be included, print AR, this is argument minus 1, this is minus 2, this is minus 3. Actually, let us count them. Alright, if I type print AR from minus 4 to minus 1, the index at minus 1 won't be included, meaning that it will print from minus 4 all the way to the end without the end element being included in the print. And as you see, minus 4 is 13, then right after it 14, 15, and 16, which is the last element, is not included. So this is how it works, and the same concept applies for multidimensional arrays. Alright, if I need to apply the same thing, okay, let's here comment. So for a multidimensional array, let's say a 2D array, at first you have, this is minus 1, and this is minus 2. Minus 1 is the entire second array here within this large array, okay? The entire second element, which is at index 1 positively, by the way. So if I print A minus 1, it will give you 4, 5, 6. Let's say out of this index, I want to negatively get 5. A minus 1, comma, then negatively, you have also here minus 1, here minus 2, here minus 3. So minus 2 would be 5. You see, the same concept applies. And so on and so forth. Okay, the same thing applies for other multidimensional arrays. Also, let's try to extract a section out of a multi-dimensional array. We will change the structure. I want to get out of the second element at position 1 the values from 5 all the way to 7. Okay, so A, at the first dimension you have 1, which is the second element because index 0 is here, and then index 1 is the second one. Then from the second, I need to get from the beginning all the way to 7. So I simply do the following. From the beginning, meaning it's enough to insert a column, and then all the way to the end, which is 8, and without 8 being included, so column, then all the way to the end position without the end position element. So either -1 or the positive index, which is 0, 1, 2, 3, the same thing. So this should give you 5, 6, 7. Straightforward. All right. Now, also another example. So let's say I need to get out of the first element, the first line, the elements 2 and 3. So let's try to do that. Print, first element is at position 0, okay? So print A, then 0, that's the first element. Afterwards, I need to get 2, 3. So how can we get that? So 2 lies at index 1 here, right? Because 0, 1. So 1, 0, 1, 2, 3. All the way to the last index. Okay, we started with index 1, then 2. Then I need to write 3 because always 3 is not included. And it will give you the elements 2 and 3. So let's check it. Fine. Now let's say I want to create an array with a specific data type. Let's clear it first. A equal np dot array. On the inside, you have the array, let's say 1, 2, 3, 4. However, although it appears to be integer, I want to cast it into a string or define it as a string. So simply you type dtype s, and if I print the data type for A, print A dot dtype, it should give me string. Let's say I need to declare an array that is integer, coded on only 4 bytes. So A equal np.array 0, 1, 2, 3, dtype equal I4, or integer coded on 4 bytes. So if I print A.dtype, integer 32, right? Because 4 bytes, each byte having 8 bits, gives us 32 bits. Also, another way is creating an array casting. A equal np.array, let's say I declared an array having the following elements: 4.33, 8.2343, 2.12, dtype equal I4. What will happen is, if I print A, it will get rid of all the float values, which are the fractions. And you see, it removed all the fractional types. Another way to do that, if I cast this array into integer using another array. So in other words, I have A is equal to this value, then B is equal to A.sType I, meaning that B is the integer value of A, the integer casting of A. So if I print B, and you see we've gotten rid of all the dots, all these values. Another example, which is interesting, is casting an array that is essentially integer into a Boolean array. Let's say you have A equal np.array starting from 5 all the way to 11. Of course, if I print the data type of A, it will give me integer by default, int64. Now, B is equal A.sType bool. Let's check it. So B is the casting of A into a Boolean array, values of an array. It gave me all true. Okay, let's change the values a little bit. So let's say 0, 1, 4, 3. So 0 has been given false. The other values are true. Alright, so let's talk about array copy, array view, and the difference between the two. At first, we will declare a new array, A equal np.zeros. This is a new function, by the way. which declares an array filled with zeros, just like in MATLAB if you're familiar with that. So I'm gonna make it 3 by 3. What this means, 3 lines by 3 columns, but two-dimensional, indicated by these two parentheses at the edge. Alright, we will start by the array view. Let's say C equal A dot view. Okay, what does this mean? C is actually a view of A. So if I type C, the first element, okay, or the first line, C0 equal 30. Let's see what happens. Print C. Of course, it gave me 30 as the values of all the elements at the first line. However, as well, if I print A, for A, you've gotten the same thing, meaning that the first line has been edited and replaced by 30. So what's happening is, you would think that C is a copy of A, but rather C through view function is not a copy, but rather a pointer to A. So whatever happens to C directly influences A. To get it in a more neat way, C0, A0, let's get rid of all the other lines. So both C and A have the same values. So if I type C0 equal, let's say, 25, rerun again, both C and A have line 0 changed. That's the difference between view and copy. However, for copy, so if I replace a view with A.copy, and let's rerun it again, and you see now only C has been changed to 25, however A still has the same value, which means C is an independent copy of A via the copy function. It's no longer a pointer. That's the main difference between view and copy. View means that C is a pointer to A, so whatever happens in C would impact A, but the copy function would create an independent copy that is standalone from A. So what you do to C would only change in C but not in A. Now let's talk about array reshaping. So if I have an array A equal np dot array 1 all the way to 6, what reshaping does is that it takes this one-dimensional array and it can convert it into a two-dimensional or more array. As an example, AR, which means A reshape, equal A dot reshape. So we have here 6 elements, right? I will make them 2 lines, okay? So 2 lines, that's the first line, that's the second line, and 3 columns, okay? Each line having 3 columns, which are the 3 elements here. So 2 by 3, and let's print AR to see what we're talking about. And you see you have 2 lines and 3 columns as indicated. Another way to reshape them, 1, 2, 3, 4, 5, 6, so 3 lines by 2 columns, and you will get them 1, 2, 3, 4, 5, 6 on top of each other. Alright, now on the other hand, let's say I need to flatten a multidimensional array. Let's say I want to reshape this array into a flattened array. So here you have 2 lines, 4 columns. And by the way, to get the shape of an array, you simply type print a dot shape. It is 2 by 4, which is correct. 2 lines and 4 columns, or 4 elements for each line or each internal array. If I type AR equal A dot reshape minus 1, let's see what happens. Print AR, and you see AR is the flattened version of A. What it does is that it takes each line, okay, and the first line will be placed at first, then the second line, third line, all the way to the end, okay, and we would get a flattened dimension. Okay, looping through an array. Now, in order to loop, it's so easy and straightforward, just like normal arrays in Python. So for I in A, which is the array, print I. Now in A, you have only 2 elements. Each internal array, each vector here is considered an element. So it will loop twice from 0 to 1, and it will print these 2 lines. Let's check it. Let's clear at first. 1, 2, 3, 4, first iteration, 5, 6, 7, 8. But let's say I need to loop for each element aside. Within each element of A, I need to also loop through all the internal elements, okay, at level 2, if you will, in second dimension. So for I in A, then for J in I, J meaning J element in I being the internal array. So now we're looping on the inside for each element inside this internal array here. Then once it is done, it will go to the second internal array or vector, print J times 10, so that you would recognize what's happening here. And you see it looped through all the values one by one this time, okay? And each iteration is for one element, for one number, not for one entire vector. Another example, let's say we have a three-dimensional vector. Starting from the beginning, you have two elements here, then another two vectors, and on the inside again, each element in this inner vector is a vector itself. So three levels: 1, 2, 3, 4, 7, 8. This is how I'm gonna loop through them for I in A. Right now, if I print I, it will give me how many elements. That would be the first element, and that would be the second. If I print immediately I within A, because A itself has two values, two elements, not more. That would be at index 0 and that at index 1. This entire array. 1, first element, second element. Now, for I in A, for J in I, print J, this will give you 1, 2, 3, 4, okay? You see 1, 2, 3, 4, 5, 6, 7, meaning each one on the inside, because here we access the second level, okay? So you count how many square brackets here. That would access what is inside the second one. But if I need to access each number, so I need to go to the third level. For K in J, print K, and you see each number has been printed aside. Joining arrays. So let's say you have two or multiple arrays that you want to join them together, to stack them together, if you will, one next to the other, horizontally or vertically, meaning one on top of the other. So here we have two arrays, one dimension each one. So in order to stack them next to each other, so as to form one larger unidimensional array, C equal np.hstack or horizontal stack A, B. Let's run it, print the array, and you have one larger array. The first one, 1, 2, 3, is stacked next to the other, starting from the first to the next in order. If I replace hstack by vstack, it should print them one on top of the other. So A would be on top and B would be at the bottom, so as to form a 2D array. So if I print C dot number of dimensions, you have two dimensions, line and column. It's a squared array, so to speak. Another way to do that is by concatenation. So let's say I'm gonna concatenate these two arrays together. Okay, C equal np dot concatenate A and B, as simple as that. And it did the same thing, okay, one next to the other. Another way to do that is to define the axis by which I need to stack these two arrays. So if I type C equal np.stack A and B, then axis equal 1. What does axis equal 1 mean? So you have the line is axis 0, okay, the x-axis in other words, and the y is the axis 1, okay? Axis 1 is the y-axis, and axis 1 is the y-axis, okay? So on the y-axis, they should stack one on top of the other, okay? Just like you've seen in vstack, okay? So it stacks them. So it stacks them based on axis 1, okay? So all right, so axis equal 1, what does it mean? All right, so axis equal 1, what does it mean exactly, and what is it gonna do? Okay, axis equal 1 is by column. because axis equals 0 is by line, the line or the x-axis, so to speak. So for axis equal 1, what does it mean is that these two matrices, okay, shall be stacked vertically one after the other, meaning that you would have 1, then 4 on the first line, 2 and 5, okay, second line 3 and 6. So let's check it actually to see how is it gonna do it. And you see 1 and 4, but on the first line, okay, on axis 1. So axis equal 1, they will be stacked vertically, something different than the h stack and y stack, by the way. Now if I replace 1 by 0 on the axis, and now you see they have been joined just like the v stack. All right, another example for h stack, v stack, and the array joining. Let's declare two multidimensional arrays. Within each array you have another array, 1, 2, 3, 4, 5, 6. b equal np.array 3, 3, okay, yeah, let's say 3, 3, 3, and 5, 5, 5. Okay, it doesn't matter. So c equal np.hstack to stack them one next to the other. Let's see. 1, 2, 3, 4, 5, 6 actually looks something like 1, 2, 3, 4, 5, 5, 6. Okay, this is the actual shape. 1, 2, 3 is on top of 4, 5, 6 here. It has been stacked next to 3, 3, 3, 5, 5, 5. So if I print a to show you what a would look like, 1, 2, 3, 4, 5, 6 on top of each other, that's a. Same thing for b, it would have 3, 3, 3, 5, 5, 5 on top of each other. So c equal np.hstack a and b, and let's print c. You have 1, 2, 3, 4, 5, 6, that's the first vector, stacked horizontally, meaning that it is laid right next to 3, 3, 3, 5, 5, 5. Or rather, b is at the right of array a. In this way, we have a and b right next to it. Meanwhile, if I replace it with v stack or vertical stack, and you see you have 1, 2, 3, 4, 5, 6 on top of 3, 3, 3, 5, 5, 5. So you would start with the first one and then vertically lay next to it downward the second array. So if we type np.stack ab and axis equal 1, let's check what happens. 1, 2, 3, 3, 3, 3, meaning that this one and this one on the second line, then this one on the second line. Okay, now in order to search for a specific value within the array and to return the index of that value, we simply type x equal np.where, meaning that give me the index for that value that meets the condition specified by me. So where a equal 3, let's say, okay, print x, okay, array 0, so at index 0 and at index 2 of the index 0, meaning the first element, okay, of this array and the third number of that element itself. So it is at 0, this one, and 2, which is 0, 1, 2. This is where it is located, so it gives you exactly the index of a specific value that meets the condition. Also, let's say give me, okay, x equal np.where a is greater than 5 or greater than or equal to 5. Let's get rid of b actually, print x, and you see now where is that exactly? If you look into the array 1, meaning the first position or position 1 or index 1, which is this element here. 1, 1 is, okay, so the first one is this block in both cases, but the second one means index 1, meaning that this is index 0 and index 1 is over here. Yes, 5 meets the condition where it is greater than or equal to 5. And 1, 2 means also 1 is this block here, that's index 1 of this larger array, and then 2 is actually the third element, which has the index 0, 1, 2. So to give you an example, you have here 0 and here 1 for the larger array, but right underneath it you have 0, 1, 2 and 0, 1, 2. So 1, 1 is this block. That's 1, 1. 1, 2 is this one. Okay, that's all of this block is 1, and 2 is the 6 over here, okay, which is the third value in the second block. Now let's say you have an array and you want to create out of it a new array that will display true if a condition is met or false if the condition is false. A equal np.array, we're gonna create it two-dimensional. So you have two other arrays as elements. Then 4, 6, 5. B equal A greater than 5, let's say. Okay, and let's print B. And you see it replaced the values by true and false based on the condition, whether it's met or not. If I place A greater than 5 is equal 0 or false, it will flip the values. So 10 and 6 will become false. Meanwhile, 4 and 5, because A greater than 5 has become false. So the alternative would be true, or the opposite rather would be true. We can also create a new array by looping through the values. So let's say B equal a new array. So for I in A, for J in I, if J is greater than 5, then append true. B dot append true. Otherwise, it will append false. So else B dot append false. And you have true, false, true, false. Okay, one-dimensional. Another thing we can do is sorting the values of an array. Let's change the values. 10, 4, 6, 1, 5, 9, 5, 4, 3, 11. B equal np.sort A, and let's print B. And you have the values have been sorted line by line from the smallest to the largest. Random arrays. So let's say I want to create an array having random values from 0 to 50. At first, I need to import the random function from within Numpy. So you type from Numpy import random. Let's say I want to get a value, random value, 1, just 1, from 0 to 50, an integer value. You type A equal random.randint 50. If I run it, and you've gotten a random value which is 28. Okay. Also another function which gets you a random value, however, this time it gets you a random float. Alright? So instead of random.randint, you type random.rand. This will give you a value from 0 to 1 float number. So 0.05, if I run it again, 0.01, it will keep giving you random values from 0 to 1. Now, let's say I want to create an array, an integer array, having random values distributed from 0 to 7. So A equal random.randint 70, and the size of the array, we'll have it a unidimensional array, is equal 8, meaning it has 8 different values. So 8 values randomly from 0 to 7. Now, if I want to have a multidimensional array filled with random values, it is similar. So, and I wanted to get integer values alone. So A equal random.randint between 0 and 100, and the size is 2, 6, meaning that it is a two-dimensional array having 2 rows, 6 columns. Random values are distributed from 0 to 100. So let's print A 98, 15, all random values, okay, and starting from 50, so 2 rows, as you see, and 6 columns, 6 values on each row. Now, let's use the rand instead of the randint, which gives you float values. So, A equal random dot rand Within rand, I want to create a unidimensional array having 5 values. Print A, and this will give you float values distributed from 0 to 1 randomly, 0.09, 0.45, etc. Also, another way to do it is creating a two-dimensional array with the rand function. So A equal random.rand, and within rand type 4.5, meaning 4 rows, 5 columns, distributed on float values or having float values from 0 to 1. And you have a multi-dimensional array of 4 rows, 1, 2, 3, 4, and 5 columns, 1, 2, 3, 4, 5, from 0 to 1. Now, let's say I want to create an array that will take its values randomly, but out of a plate of choices. V equal random dot choice, and here I will give him the slate of numbers out of which he needs to choose. In this format, he will give me only one value distributed, randomly chosen among the values given within this inner array. So if I print V, he will definitely give me one of these values. And it gave me 9, which is the second choice. However, if I need to create an array, let's say multi-dimensional array, out of these values randomly picked, V equal random dot choice 4, 5, 9, 2, 6, 8, and I will give him the size equal 2 rows, 6 columns. Print V, and he will create a matrix, 2 lines, 6 columns, randomly picking the values out of this array. This is what choice means. It means that the random numbers are only taken from this plate, from this basket, so to speak. I can also create a unidimensional array. In such case, I type size equal 10, and it will give you 10 values or 10 elements within a one-dimensional array taken randomly out of this inner array. 8, 5, 9, 9, 8, 9, 2, 2, 4, 9. All of them are taken from this array. Another thing we can do is creating an array that will randomly pick one of the values cited here, one of the options, however, based on a specific probability. So some of the numbers will have higher probability than others within the choices. So let's say Z equal random dot choice. I will give 2, 8, 5, 1 are the different values, comma P, which stands for probability. Probability for each number respectively. So the first one will have a probability of 0.4, 0.2 for the second, 0.1, and 0.3. Each probability for its related number at the same position. 2 has a probability of 40% of being chosen, 5 a probability of 10%, 1 a probability of 30%, and then I define the size, let's say a unidimensional array of 10 values. Print Z. Now, it might appear that this probability is not working since you have 5, which has only a probability of 10%, has been chosen 2 times at least. However, this will become more apparent, more prominent when you have larger arrays. Array shuffling. So let's say ARR equal np.array 1, 2, 3, 4, 5, 6. Shuffling means mix all these values together in a way to disturb their order. As you see here, they are ordered from 1 to 6. When you shuffle, they will change their order randomly. 6 might appear in the middle, 1 might appear at the end, etc. So to shuffle, you simply type random.shuffle array, and let's print array. Their order has been disturbed. So another thing, let's use permutation function. Permutation would permutate these values, okay, would swap them, so to speak. So new array equal random.permutation array. And let's print this new array. And you see they have been permutated, okay? They have been swapped. Now let's say I want to distribute values based on binomial distribution or normal distribution, or let's say I want to plot the values at first. So I need to import another library which is called Seaborn. Import Seaborn as SNS. SNS, by the way, is an alias for Seaborn, so that you won't have to use the word Seaborn every time you want to call a function. It becomes a short-handed Seaborn prefix. So let's delete these values at first. As you see here, it's apparent that I don't have the Seaborn library. I need to install it from the packages. And you see there's a shortcut for that. I can simply click on it, or you go to Python packages, you look for Seaborn, and once found, you can install it from here. However, it's being installed right now. Another library, I need to plot the values. I need to import Matplotlib. Import Matplotlib.pyplot as PLT. It appears that we already have it. Let's use this to plot, and plt.show, meaning show me the curve for that. Yeah, you see? And we've plotted the distribution for that array. You simply type plt.show and it will give us the curve created by SNS. This is what it does. It plots data on a curve, on a graphical visualization. Now what this curve is doing, it is representing the values or distribution of values based on their occurrence within the array. So you have the density of occurrence of 0 is 0.1 or 15%. 2 the same way, 4, 5, 6 the same way almost, and other values do not exist within the array, so their density or occurrence is 0. Now let's say I want to change this array a little bit. Let's clear. Okay, 0, 1, 1, 1, 4, 5, 6, and let's plot it again. So you see this time you no longer have that normal distribution, so to speak, because the density of 1 is much higher than the density of other numbers. Other numbers might have the same almost distribution, the same values. However, the probability for 1 or density occurrence for 1 is much higher than the others. Okay, you have 4, you have 5, 6, almost the same thing. Of course, we don't have values outside of 0, but 1 is the highest one. Alright, let's create a normal distribution having a size of 1000. So, sns.listplot random.normal distribution of random values. Size equal 1000. Histogram equal false. Let's turn off the histogram. And then plt.show. Alright, let's create a random exponential matrix. So x equal random.exponential. Now, the first argument is scale. By default, it is equal to 1, which is the inverse of rate or inverse of number of occurrences of a specific value. So, scale equal to, let's say, and size, which is the size of the matrix, by the way, is 2 by 3. So 2 rows, 3 columns, print x, and this is the created matrix. Now let's plot this matrix. So sns.listplot x and then plot.show, and this is the matrix. This is the distribution of the matrix. Most values having the highest density are between 0 and 1. Alright, and you have also occurrences between 3 and 4. At the end, there are other types of distribution that follow the same pattern. We won't go through all of them, but it is almost the same concept and the same way of programming them. Alright, so let's work with universal functions. Let's say we have two arrays. So what kind of operations we can do with them? All right, A equal np dot add x, y. Adding these two matrices element by element, one by one. All right, so 3 plus 7, 3 plus 7, 3 plus 7. Let's print A. And you have 10, 10, 10. Okay. Let's change the values a little bit. So 15, 10, 3, 8, 2, let's say. Okay, another operation is multiply. So A equal np dot multiply xy, print A, and it will multiply these two matrices element by element, or these two arrays. So 30 by 4 gives you 120, 15 by 3, 10 by 8, 80, 8 by 2, 16. Another one is divide. It will divide x by y. So let's check it. And of course you will get float values. 30 divided by 4, 15 by 3 will give you 5, of course. 10 by 8, 1.25, and 8 divided by 2 will give you 4 float results. Another one, subtract, which is x minus y, by the way, but it is doing it element by element. So 26, 12, 2, and 6. Okay, so let's change these two vectors a little bit. 4, 2, 10, 3, 5. Okay, and let's right now get the power, meaning x power y. So it will place each element of y as the power of 4. So 4 to power 2, 2 to power 1, 10 to power 3, which will give you probably 1000, 3 to power 2, etc. So we will call it P. P equal np dot pow, or power x comma y. Print P. And you see 4 power 2, 16, 2 to power 1, 2, 10 to power 3, 1000, etc. Another operation related to division is mod or modulo. So what this will give you is the remainder of the division. So 4 divided by 2, it will give you 0. 2 divided by 1, also there is no remainder. 10 divided by 3, remainder is 1. Another way is np.remainder xy. It will give you an error y because you're dividing by 0. However, for the modulo, it was more tolerant. Okay, it gave us 0 here. Alright, so rounding and truncating. So let's say you have A equal np dot trunc, and we have floating values 1 point or 2 point something. So let's print A, and it will truncate all the floating parts. It means that it will remove all the fractions from these numbers, and you will get 3 numbers as if they were integer. It's like casting into int, however, the data type is still float for A. Another similar function is A round. Now, the difference is what A round does, it will round these values based on how many decimals you need to get after the dot. Okay, so let's say decimals equal to, you will get 2 numbers after the fraction, after the separator. So let's test it. You see, since after 3 there's a 9, it will round it up. So you will get 2.44. If you had a value less than 5, you will get 2.43. Here as well for the third value, 1.33, because after 2 you have 9.8. Alright? Okay, another type of functions is the trig functions. Okay, trigonometry functions. So let's say you have a matrix or an array which is an angle array. 20, 30, 90, 10, 60. Okay? And we want to evaluate the sign of each of these angles. So SI equal NP dot sign angle and print SI. So it will evaluate the sign of all of these angles. Another function is the cosine of an array. So CO equal NP dot cosine angle and print CO. Let's see what we get. And here in the second array you have the cosine of the above angles. Also you have the hyperbolic sine, cosine, and tan. SH equal NP dot sine H angle, print SH. Okay, NP dot cosine H, NP dot tan H, hyperbolic tangent. And let's work right now with the logarithms. So for the logarithms, okay, we will change the angle here to x, let's say. And we're gonna evaluate the log base 10 for the values mentioned here. Log base 10, by the way, will give you the power of each of these following values. So 10, 100, 10,000, let's say, or whatever, and 1. We'll call it L equal NP dot log 10 x print L. And you see here, because the power is 3, 10 to power 3, the log 10 of 1000 is 3, 10 is 1, of 100 is 2. It's actually counting the number of zeros in such case. Here you have 4 and here 0 because it's 10 to power 0, that's why. Finally, another example. Let's say I want to get the inverse of an angle, so our sine. You have the sine of an angle. I want to get back the angle value out of the sine. S equal, let's say, minus 1, 1, 0.1, 0.01, 0.002. A equal NP dot arc sine S, and let's print A. And you've gotten the actual angle for these values, okay? Or let's say NP equal arc 10, arc tangent of S, minus 0.7, 0.009, etc.